Okay, thank you. So this topic may not be, how to say, is it very precise? Even I don't know. I just like to talk something from concerning my work and the recent work may not. I try to answer the question why we can achieve some important result in the distribution of primes, in particular the twin prime conjecture. And also I would like to mention a fierce mental work by the Professor Maynard in England. Yes, also is in this field, twin prime conjecture. So we start with this one. We say let P denote a prime number. So sorry, here we didn't have 0. It should be 0. If n is a prime P, then theta n is equal to 1. Otherwise, it is equal to 0. Sorry about that. I missed this one. Okay. So the theta function, it is the characteristic function of the primes, right? Then we know the twin prime conjecture asserts that there for infinitely many natural numbers n, both n and n plus 2 are prime numbers. If we try to formulate such a conjecture, that is just if theta n plus 2 minus 1 is strictly greater than 0. That's the same. And but in practice, if we try to formulate it further using some formulas so that we using the certain way in analytical number theory, we can evaluate something. It is reduced to some sum, to evaluate some sums. So for any sufficiently large real number x, we wish to find one n such that between x and 2x, both n and n plus 2 are prime numbers. So it is, we use this way. The question becomes, can we find some non-negative number an, n is between x and 2x, such that this sum is strictly positive? We only need to prove it is strictly positive. If this is positive, then we know that at least for some n, this term is positive. And since we already assume a sub n is non-negative, but if the product of this term is positive, that means an can never be 0. So an is positive. So just like this, theta of n plus theta of n plus 2 minus 1 is positive. Therefore, n and n plus 2 both are prime numbers. And since x is arbitrarily large, so that means always there is a pair of prime numbers greater than x. So in other words, they are infinitely many twin primes. So we just need to find this. That is our approach in a standard way of in analytical number theory. I don't know if we try to approach it using algebraic number theory, using something else, that could be a different formulation. But it is a reasonable formulation. And so now the question is, how can we find such an an? And right now, can we find such such an an. Unfortunately, we're unable to do this. But so the last word I say, unfortunately, we're unable to achieve one right now for a certain essential reason. So now let's consider a weaker form of the twin prime. That was before my work, more than maybe in 1990s. Three mathematicians, Goldstone, Pins, and Yildirim. Goldstone is in America, Pins is in Hungary, and Yildirim is in Turkey. They consider a weak form of the twin prime conjecture as follows. First, we fixed finite integers. This is fixed. Just in our argument, these are just just regarded as constants. Then the search non-negative numbers an such that this one. So if k equal to 2 and n1 equal to 0, n2 equal to 2, that was the formula 1. So we find that this should be a general form of, not general form, because it is weaker. Anyway, let's consider this one. Also, if 2 is true, that means at least one term is strictly positive. Then there is n between x and 2x, such that because the an is non-negative, here if it is this term is positive, then a sub n must be also positive, such that theta n of n plus 1 plus theta of n plus 2 plus plus theta of n plus nk minus 1 is strictly positive. Here, everything is integer, right? So we say this inside this pair of brackets, it is positive. Then this sum, the theta n plus 1 until theta n plus nk is at least 2. Among these numbers, at least 2 are prime numbers. Then that means because we require these n1, n2, these are distinct. So at least 2 primes, the gap between these 2 primes is bounded. It is less than or equal to n sub k minus n sub 1. That, although we are unable to prove the twin prime conjecture, but this weak form, for example, n1 is equal to 0, nk is equal to, what's my first result is 70 million. Then there are infinitely many primes. The gap between these 2 primes, the pair of these 2 primes is less than 70 million. This is our basic idea. We are looking for some non-negative numbers a sub n such that 2 is true. It is possible to achieve such a result as it is weaker than the twin prime conjecture itself. Now, let me describe something. I didn't have time to put everything in this one. The top is just explained always. In that way, we can find the bounded gaps between prime result, like this. Now the question is first, how to choose the number a sub n only requirement is the A sub n must be non-negative. We don't have other thing. Then there are many, many choices. And in fact, in history, that starting from maybe 1980, 18th, very early, more than 100 years ago, when Norway mathematician Brown created his sieve method, the essential question is also how to construct the A sub n, at least the A sub n must be non-negative, and also there are some other conditions. Brown's method is a combinatorial identity involving the so-called Mobius function. But that's very, very complicated, and also in practice, it couldn't give some very good results. Then later on, another Norway mathematician, Selberg had a very nice, but also simple idea. We need a sequence of numbers, A sub n. The first requirement is A sub n is greater than or equal to 0. Selberg said, okay, let's introduce another sequence of the real numbers, Bn. Bn only requirement is these should be the real numbers. Then we take An equal to Bn square. That's it. This is Selberg's idea, and then later on in the sieve method, always, whenever we try to find some non-negative sequences, we take it in this form. And the question is reduced to determining what is Bn. Then how to find the Bn? The Bn is chosen by Goldstone, Pintz, and Yildirim in this form. In number theory, it is always like this. We need to choose a certain sequence satisfying some condition. But at the very beginning, we don't know how to do that. We may test a lot of things. So the first test is take it as the square of another sequence. Then another sequence for some deep arithmetical reason is chosen in this way. Here, ft is a function in D. Usually, ft is also a complicated one. Involves the logarithm of D in that is analytic aspect, and also the arithmetic factor. It involves the Mobius function. So I'm not going to write that down. D dividing P of n. P of n is given in this way. And also D has a constraint. D is less than or equal to another parameter, which is capital D. Then the evaluation, whenever we choose the A sub n as equal to D sub n squared, D sub n is take that form. The evaluation of the sum 2 consists of two aspects. One is the major term. The major term, we have standard way to evaluate it. But the requirement at least is because we need to prove it is greater than 2. I'm sorry, greater is non-negative. Totally the sum is positive. So at least we require that the coefficient in the major term must be positive. If we get the coefficient is negative, it is possible, then this is useless. For example, let's say if we try to say we are given a large even number n, we say Dn equal to the number of the solution P1 plus P2 equal to D equal to N. The Goldbach just saying that we need to prove this solution, the Dn is positive. But in practice, if we couldn't reach what we need, we just find a lower bound. It is greater than some negative number. Is it true? Of course it is true. It is trivially true because the solution, but what we need is to prove it must be positive. If we can prove it is greater than a negative number, then it is true, but it is useless. So here, one requirement is the main term in our result precisely is the coefficient of the main term in our result must be positive. On the other hand, it is like this, the parameter capital D, the larger is D, the better is the main term. But D cannot be too large because if D is too large, there are too many terms, then the arrow term, we are unable to control the arrow terms. But D cannot be too large. Otherwise, one is unable to control the arrow term. So how large the parameter D could be is a deeper problem in analytic number theory. Actually, this depends on some deeper results on the distribution of primes in certain arithmetic progressions. Then there is a okay. This is, as I mentioned, the so-called Bambira-Vinogradov theorem on the positive distribution in arithmetic progressions. The Bambira-Vinogradov theorem guarantees that whenever the D is less than a certain power of x raised to 1/4, because the an takes the square of bn. So actually, this exponent in Bambira-Vinogradov theorem in its original form is 1 second, is 1/2. But that doesn't matter, the different way to write down it. So if capital D is less than this power of x, we are able to control the arrow term, but unfortunately, the work of the Goldstone, Pince, and Yildirim shows that with an given by 3 and 4 in this form, the main term is positive only if D is greater than this power of x. So now we are reached to a critical point like this. In order that we are able to control the arrow term, in evaluation of a certain sum, always in analytic number theory, we have two parts. One is the main term, another is the arrow term. At least the arrow term, the contribution, if we take the absolute value, cannot be larger than the main term. Otherwise, this is useless. In order that the arrow term is controlled, we can control it. It is less than the main term. D must be less than or equal, could be equal to x raised to 1/4. On the other hand, in order that our result is useful, it makes sense. we required that the main term, the coefficient of the main term must be positive. In order that the coefficient of the main term is positive, we must have d is greater than this one. That was before my work, the problem, the bigger problem they had. They cannot cross this one. Although as they describe, only if they can improve the 1/4 to 1/4 plus epsilon just a little bit, then the bounded gaps of prime number problem, the weak form is proved. And here I use it to just say, and also it was conjectured that the d equal to x raised to 1/4 here, but if in the original form is the exponent is 1/2, could be broken. We can get something better than that. And there is another conjecture, the Halberstam-Eliot conjecture, said it could be from 1/2 to 1 minus epsilon. And also there are a lot of work towards this direct. But this one seems extremely difficult, even if the generalized Riemann hypothesis cannot help. Because till now, even if we assume the generalized Riemann hypothesis, that means the zeros of every Dirichlet L functions is on the critical line 1/2. Even we assume that conditionally, we are unable to improve this from the 1/4 to 1/4 plus epsilon. Then what I did was the arrow term. First time I break this 1/4 boundary with some constraint on the variables d. I improved the arrow estimate and show that the argument is a variable. We can replace d equal to x raised to a exponent, which is slightly less than 1/4. Whenever the arrow term is improved, we can take d larger than everything. This implies the 2. This was proved with in my choice, the n1 is equal to 0, nk is a number less than 700. So that solved the problem of bounded gaps of primes. This result is an essential improvement. Maybe in history is the first essential improvement, breaking the boundary given by the Bambino-Vinick-Dirac theorem, and it has its own importance like this. And also I can say our argument combines various. How can I break this to the x raised to delta greater than 1/4? It is very interesting. In the history of analytical number theory, the Dirichlet L function was first introduced by Dirichlet himself. Try to solve at the very beginning, he just tried, and he was successful to prove that there are infinitely many primes in a arithmetic algorithm if the difference A and D are coprime. P is congruent to A modulo D whenever A and D are coprime. And then in his direction, until Chen's result of in Goldbach conjecture, they follow this direction. Reduce the distribution of prime numbers in arithmetic algorithms to the Dirichlet L functions, the zeros of Dirichlet L functions. But in my proof, it is also an interesting one. I combined various classical results in analytic number theory, and also we use new techniques from algebraic geometry. I use another type of the Riemann hypothesis. Riemann hypothesis for variety over finite fields. That was proved by Deligne. That's the so-called, it's called the Weil conjecture. Already proved, we conjecture. Already proved by Deligne. So I can use it. And I use a special case. That is for the for a special type of algebraic surfaces. That is the deeper result, the deepest result in my proof. So this one. Then let's recall something. We come back. At the very beginning, I say these works. I just follow formula 3 and 4. AN is chosen as formula 3. BN is in such a form. These are just works of the Goldstone, Pincer, and Yoder. Then we have a question. Can we choose different forms of the coefficient AN? At least we know at the very beginning, we don't have any other requirements. We only say AN must be non-active, that's all. Then that was later on, the work was greatly improved by Maynard. His major contribution is to improve the choice of the coefficient Bn. He also used formula 3. An is equal to Bn squared, but Maynard chose the Bn in this form. Here we can see that the G is a function in several variables, in k variables. So this could be just like our choice, the formula 4 Bn. It looks like just a one-dimensional choose. We take the product n plus n1, n plus n2 till that. We take the product. But Maynard's choice looks like a generalization of our choice. Then, do we have any constraint on these the D1, D2, dk? Yes, it is. The constraint is that the least common multiple of D1, D2, dk is less than capital D. And in his original work, he still takes D close to x raised to 1/4. He didn't go anything more about the error terms. Later on, we know that Terence Talk organized a project online, try to improve these bounded gaps, the constant as possible. So at the very beginning, my work was given the constant that the gap is 70 million. Then we have two directions. One is to improve the choice of the main coefficients Bn. Bn now was given in the form of Maynard's paper. Another one is also to improve the arrow term that is bounded by the capital D. Capital D, already I break it to D is greater than x raised to 1/4. So in these two directions, both 5 and 6, this is Maynard's contribution. This was my contribution. Both of these are used and combined. Then till now, the best result on the bounded gaps between primes is 246. Then we may ask further, can we improve it? It is possible, but in my feeling, in this direction, still we are unable to reach the original twin prime conjecture. So this is what I can say like this. Thank you.